Ah. Other people outside. Hi. Okay, so are you hearing me too much, or it's okay? It's okay. So I don't have the link yet for the, but it's too much for me. I don't have the. Just a minute. I think there is no volume here, or maybe it's here. Just put it here. So I don't know if the videos are, if you got a link or something to the videos of this year, but I heard from Nir, that's the guy that's organizing it, that it will be on shortly. So it's a very, very helpful tool. Obviously, like to go over the classes like in when you're practicing for an exam or something like that. So that's one of the good reasons, and that we have this camera, and also it's better when you can hear the person who is presenting. So you should insist on the lecture to wear this, although a lot of people don't like it. But it's really important, because otherwise you really can't hear what they're saying. And so, yeah, how was the reading or going over the presentation or something like that? Did you experience some difficulties, questions? I noticed that you were a little bit silent in the last class. In the following classes, we're going to be a little bit slower. Okay. So I hope that you're not afraid like to ask stuff that you don't know, because this is the whole objective of this course, is to get you acquainted with the terms of biology. So in general, if there's something that is not clear, then ask. Okay. Also, I see that we are now starting to dilute a little bit. Which is generally a good thing, and so I'll start by asking you your names, okay? And we're gonna do a quick name round, and everybody. So you need to tell what's your name and what is your what's your background, okay? So what did you do in your bachelor's or master's or something like that? So my name is Nadav, and I'm in the lab of Professor Hamana Sorek, and in my PhD, it's like my 5th year of the program of the ICNC, and but in the PhD, and the official PhD is like the 3rd year, and before that I did a bachelor's in cognition and biology in the Hebrew University, and that's it. We can go from here. What's the name again? Yeah. I didn't understand again. Leah. Okay.
I'm Gal, and I have my background in mathematics from Bar-Ilan University.
And Tomer, I did Bachelor of Degree in Physics.
And Marie, graduate in psychology.
And Helix, I'm here in biology.
I'm Ben, I'm doing my bachelor's
Okay, great. So now that we all know each other, like Forrest Gump says, we're not strangers anymore. So you can feel more comfortable. Anyway, as you could see on the website, I gave you questions that are in the type of question that you already also have in the exam, that are supposed to guide you on what is the level that we are expecting from you, and also to help you in the reading of the chapter. I know a lot of times, especially in ICNC, you don't have a lot of time to read a lot, or you don't have a lot of time in general. So this will also help you focus what is the level that you need to understand when you try to read the chapters. So we'll just go over quickly over these questions, and if there is any questions or something that we don't know, then we'll discuss it. So what is the cellular function of adenosine in what cellular function is the adenosine base involved in? Okay, so you remember that we saw actually two forms of adenosine base. So one of the two forms where this molecule can be in. Does someone remember where? ATP, that's right. Which is for what is it good for ATP? What did we study? About energy transfer. Yeah, it's the energy coin of the cell. And the second one? Not amino acid. It's a nucleotide. Okay, it's part of a nucleotide. Thus, it's involved in what we call information storage, because it's involved in it's part of the nucleotides that we have for DNA. Okay, so the information of the cell is stored in the form of DNA. So the correct answer here is B and C, or F. So here we ask you to link between monomers, between the building blocks and the macrostructures that they make. So what are the building blocks that form RNA? Do you remember?
The nucleic acid.
Right, it's nucleic acid, or what we call nucleotides. So we have here nucleic acids. You see, and
Although, if I understood correctly, so RNA and DNA are actually types of nucleic acids. It's not really true to say that these are the building blocks.
No, RNA and DNA. When we say maybe the better way to form this would be we have no way of saying plural of DNA and RNA. Okay, when you talk about a nucleotide, it can be a nucleotide of DNA and a nucleotide of RNA. But when you attach a lot of nucleotides, they are still termed RNA, and when you attach a lot of nucleotides of DNA, they are still termed DNA. Okay, so it's not like in the next example that when you see where you have a distinct general name when you attach all the building blocks together, but still these are the nucleic acids, although they are different for RNA and DNA, because what we saw is that one of them, the DNA is missing one of the oxygens, so that's why it's D-deoxy, and that's the name D. So instead of RNA, so yeah, I think I answered, or no?
DNA helix, for example, is
a lot of nucleic acids connected together. Okay. But this, in general, will be when you have a single nucleic acid, then a lot of time you will never. Normally, people will not call it DNA or RNA. They would say this is a nucleic acid, or a nucleotide, or an RNA nucleotide, DNA nucleotide, or something like that. Okay, so but the most important thing is that for you to understand that RNA and DNA are composed of long chains of nucleic acid. So the cell membrane, what is it made of? You said something with phosphor. That's good. So they're made from phospholipids, or the cell membranes are actually composed of a complex of phospholipids, or phospholipid bilayer. that, as we saw, it's an amphipathic molecule that has a polar end and a hydrophobic end, and these form a double layer of phospholipids that actually cause an isolation between the extracellular surface or extracellular area and the intracellular area, like inside the cell and outside the cell. Okay, and we have what is composed, like what makes a polypeptide. In this case, it's amino acids. What we're going to talk about today actually is a lot about proteins. Okay, so proteins are actually polypeptides, and that are just made of a lot of amino acids and that are connected together. This is actually a peptide. I will not call it a polypeptide because you will see later why, but this is like a molecular model of a chain of amino acids. And that means I'm too long on one slide. Can we see now something? No, shit. Okay. So we'll see it later. And the easiest example, if we have a lot of monosaccharides, what is the molecule that we're going to get? So a polysaccharide or a polysaccharide chain is composed of a lot of monosaccharide units. And okay, so is this clear, this building blocks? Because this is very important. This is something like very basic that you will also be very useful for you to understand, like papers and stuff like that people are talking about that. So these are the four main components that we have in the cell. Okay, we have the phospholipids, we have the monosaccharides, we have the nucleic acids, and we have the amino acids. Okay, so these are the basic building blocks of what we have in general in organic chemistry, at least in biology. Okay, so this is also very important for neurobiology. What type of chemical interaction exists between the sodium ion and water? No, you're right actually. But
Your eyes said something different.
because I tried to alter your confidence, okay?
You read it.
So the type of it, we also talked about it. There are all of these things. We have slides that are talking about these exactly about these questions. What happens when an ion actually enters aqueous solution or something that has a lot of water in it? Is that the water, because it's a polar molecule, interacts with the ion, okay, through ionic interaction, and forms like kind of a cluster around the ion. Okay, so if you want me to, I can remind you. Okay, so this is like a example of another ion, but doesn't really matter. It's also a cation, an ion that is positively charged, so it is stabilized or covered with a lot of water molecules surrounding it. Okay, so we call it like an ionic interaction. Yeah.
Is there such a thing as hydrophilic interaction?
It's a good question. When the term hydrophobic is a lot of times referring to the hydrophobic effect that we also talked about the fact that you have like water cages that because of these cages it tends to hydrophobic molecules tend to form like clusters. So normally it's not like when we talk about ionic, it's reserved to ions, and hydrophilic and hydrophobic we will talk about when we talk about larger molecules and their interaction with water. But let's say in an exam, that's a good. Let's say 50% of you or 30% would circle this. Like if we had both of them, then you would say you have to say I don't know. But let's say you could circle more than one answer, and a lot of the class would circle this. Then I would probably cancel the question because it kind of is hydrophilic interaction, because the term interaction is something very general also. Okay, so. Last question, monosaccharides differ from one another? Right, yeah.
Sorry, I have a question about the interaction. So I understood that there is the covalent bonds and those that are not, and I didn't understand what determines whether a specific interaction can happen between specific atoms or not. Is it the characteristic of a specific ion?
It's the characteristic of a certain of the atom. We're not getting into that. But this is like there is something like I can refer you if you want to like reading material about that. But it's like we said in the previous lecture, we said that every atom has a specific type of connection that it tends to form, and this is because of the amount of the electrons that it has in his valence shell, like in the and so there is a tendency, actually, intrinsic property of the material of the atom that determines how many bonds it creates, and also the tendency to form bonds. But actually, these covalent links are actually, a lot of times they are formed. The fact if you will have a covalent bond or not is more of a question if you have a molecule that will form this bond, or if you have that. We're talking about it in the not today but tomorrow, about certain enzymes that form certain bonds. Okay, so let's say the bond between a polypeptide chain or in a protein. So this specific bond is catalyzed by specific enzymes. Okay, or by the ribosome, if you heard about it. Yeah. I think like it's something. It's like a general. You're asking very good questions, but a lot of times the answer is very general. Like it's very hard to.
I understand the question is also very wide, but the chapter also mentions specifically, for example, the Untitled Chapter.
Yeah.
So it mentioned that it is especially efficient for some cases when the atom cannot make other interactions. So
Van der Waals interactions are something very. Actually, there's something very general. Like if there is close proximity between two atoms, any two atoms, basically, there can be like Van der Waals interactions between them and forces. So it's something very not. There's not a rule to Van der Waals interaction like in regard to that. That's why the gecko can climb any surface. Okay, in general. Okay, even very flat glass. Okay, so just to finish with this. So anybody knows the answer to this question? Right, all of the above. Okay, so we saw that there are sugars. Actually, what determines a sugar is just repeated units of what we said, carbon and water molecules that are just repeating and connecting between themselves through the carbon. And so there can be variance in the number of carbons in the molecule. Some sugars have 5 carbons, some sugars have 6 carbons, some sugars even have 7 carbons, it depends. And bond conformation is actually what determines what is, if we have a sugar that has 6 carbons, so a lot of time just the conformation of the bonds inside the molecule will determine if it will be like fructose or sucrose or something like that. And ring size also, and I'm not going to discuss this so much, and the polysaccharides they form. Obviously, different building blocks build different polysaccharides. Okay, build different. If we're talking about cellulose or we're talking about glycogen, so it's different building blocks that are building a lot of times these structures. Okay, great. So I'm going to publish a new set of questions today after class, so you don't have to wait so long, don't have to be in tension. I know that you're eager. So, what I actually wanted to talk to you a little bit before is, before we start today's class, is the term, we discussed before about that if we were talking about amino acids, and so they can have two conformations, like I told you. They have the D and the L conformation. So a lot of times it's very hard to see it, so I brought you like models. So this is like a model of an amino acid. We have the alpha carbon, what we will say. This is the black, okay, which is attached to one small hydrogen, which is the white, and this is a representative of a side chain, okay? So this is actually what differs between different amino acids, okay? So all of them have this structure, and this is variable between different amino acids, and as you probably recall, we have 20 amino acids, some of them are hydrophobic, hydrophilic, and so on. So we have the alpha carbon, we have the carbonyl atom that is attached. If it's inside a polypeptide chain, then it has only one oxygen, and the other side is the peptide bond with the other amino acids. But if it's in the free form, then it has two oxygens. And on the other side, we have the amide group, which is nitrogen, which is blue. Almost all the time, hydrogen is red, carbon is black, what did I say? Oxygen is red, carbon is black, hydrogen is white, and nitrogen is blue. Okay? They're not actually blue. Okay? Although maybe they are, but nobody knows. So, but they don't have any color because they're basic atoms. Anyway, so, and here the nitrogen has 3 hydrogen atoms, which it will only have 1 in the state where it's connected to, where the link is continued to other amino acids. Okay? So, we have this amino acid, and we have the exact same amino acid, but as you can see, they're like mirror images of one another. Okay? So there's no way I could overlap these two. That's also one of the concepts that I want to tell you, that we have only, so I'm not expecting you to remember which one is the D and which one is the L, just to, if you want, then there's a simple method, is if the hydrogen is pointing towards you and the side chain is pointing up, then the one that you're holding, actually, it's a stupid method. Never mind. Forget about that. It's stupid. Anyway, only one of them exists, actually, as very abundant, or exists in nature, which is the L conformation, and the other one is really rare. Okay, really rare, and can also be toxic in a lot of examples where pharmaceutical companies don't know their organic chemistry. So one of the examples for that is the sad example of thalidomide. I don't know if you heard about it, but generally in the United States, somewhere along, I think the 50s or 60s, 70s, I don't remember exactly, but there was a pharmaceutical company that came up with a product that helps for nausea during pregnancy. Okay, so one form really helps with the nausea, and another form, which actually the only difference between these two molecules. Here, in this type of molecules, they're referred as R and S, but basically there are just conformation changes. And this is also like how you denote this. If you have this mark, it means that it's towards us, and if you have this mark, it's toward inside the board. Okay, so you can see it in here, like this is pointing towards us, and this is pointing towards the board to the back. So because of this small conformational change that the company didn't really monitor for, this actually causes very, very severe defects in the development of the embryo. So a lot of children were born without certain limbs, or without fingers, or stuff like that. So this small conformation, although the molecule is almost identical, can cause really severe effects on the biology. Okay, so in this chapter, it is going to be based on the Lodish chapter 3. And now we're going to talk about protein structure, and we're actually it's like kind of introduction to proteins, okay? So we're going to skip the part about how proteins are made or how they are born, and we'll talk about it in 2 or 3 classes about that. And we're going to talk about once a protein is made, so what happens to it, or how do we define different components or the structure of the protein. Okay. So we're going to talk about the hierarchical structure of proteins, meaning like the different structures that they form. Like the most simple structure is just a chain, which is like and then it has, obviously it doesn't stay like that in the cell. Like in the cell, it folds in a lot of very exact ways to form. So in the end, it will form like into a functional unit. So we're going to talk about that in the folding, modification, and also we're going to talk about the degradation of proteins, like how proteins are destroyed or recycled. I think today maybe we're going to get to enzymes, but probably not. In next class, we're going to talk about molecular motors, actually proteins that move stuff around the cell, which are really cool, and how proteins are regulated, and lastly, and maybe it's also very important, to how do we identify, how do we study, how do we investigate proteins? Okay, so how do we isolate them or purify them? How can we detect and characterize the proteins? So the first thing we need to know about proteins is that they have this kind of hierarchy of arrangement or structure, in that if I show you like a polypeptide that is made of a lot of amino acids, and it's in its linear form, like here, then I'll say that this is like the primary sequence, or just the linear sequence of amino acids that are linked together. Okay. And the secondary structure is what we refer as local folding, and we will see that there are certain structures that proteins that amino acids or proteins tend to fold into. Then we have the tertiary structure, which is actually the end of in more of a macro scale of how the proteins fold, how every protein folds differently and into its specific and unique structure. Then, and it's important to say that all of these structures, primary, secondary, and tertiary, we're talking about the same molecule. Okay, so we're talking about the same polypeptide chain, and we're just describing the way that it folds. Okay. It's not a chemical change. It's just kind of if you take like a spring, okay? If you take like a spring and you or a piece of thread and you hold it like this, and then it's linear. But if you put it in an environment where you have forces acting on it, then it will fold in a specific way. It will not stay like in its linear form. So a thread is a very simple example because all the molecules are more or less the same along the thread. But here, the three-dimensional structure, which is the secondary and tertiary, are determined by the identity of the amino acids. So different amino acids, because of their interaction between the side chains, can cause different type of folding. Okay, and we'll see it. We'll talk about it in detail. So these are the three definitions of when we're talking about folding inside the same molecule. Then we have the quaternary structure, which is a lot of time we have, especially in neurobiology, when we're talking about receptors and channels and stuff like that, we have a lot of proteins that are made of a lot of subunits of similar proteins, but they're not the same molecule. But you can think about if you have protein left hand and protein right hand, so they can come together to form a channel, okay, or a functional unit. But in that sense, they're not the same molecule. So that will be like the quaternary structure. And we have the last scale, which is the supramolecular. When now we're not talking about different subunits of the same protein, but we're talking about different proteins that are acting together to do some kind of complex biological function, okay, or complex molecular function. And we're going to talk about that also. So it's very important to understand that the information for the way that a protein will fold is dependent or determined by the sequence of the amino acids. Okay, so different amino acids will cause different folding. So, as I said, the primary structure of peptides or proteins is just like a linear form when we're talking about the amino acids. So here we have 3 amino acids. Each of them can have a different side group. Like here we have 4 amino acids in this model. Okay, so it's supposed to be something like this. And it's very important to understand that what is the nature of the bonds that we have here. So how can this structure fold? So, for example, something that are rigid, like I told you before, that are intrinsic to the atomic property of carbon, is this tetrahedral formation. Okay, so this, like in my model, it can't shift too much. You can't change the angles inside the tetrahedra unless you have like a triple bond, and then it's planar. Okay, so if you have 4 molecules around the tetrahedral, here I don't have any flexibility. Okay, for like doing all sorts of movement like that. So the angles between the tetrahedral are constant. Also, the bond between 2 amino acids, which is called the peptide bond, is not strictly a double bond, but it's something in the middle. It's kind of it's something that we're not going to discuss, but it tends to be pretty rigid. Okay. So the bonds that actually can change, if we're looking at inside amino acids, are mostly not the bonds, the angles that can change between when a linear form of amino acid, when it needs to fold, are 2 angles that we're going to discuss in the next slide. Another thing that's very important to understand is that a polypeptide has directionality. Okay, so a lot of time people will say from N to C. Okay, so N is the nitrogen that we have this will be the N terminal, and the C terminal will be where the carbonyl carbon is in the end of the chain. So this also determines like the directionality. A lot of time you will see arrows on where's the beginning and the end of the amino acid chain. So N, you can remember it as nu. So when a protein is made, it's actually made from the first thing that comes out is the N terminal, and then the last thing that comes out is the C terminal. Okay, of the ribosome, the machine that makes these polypeptides. And we talked about that. When we're talking about size or weight of proteins, normally the unit that we're going to use is Daltons. Okay, so we can say that one protein, the weight of the size of the protein is 75 Dalton or 1,000 kilodalton or megadalton to describe the size of the proteins. And Dalton is actually atomic mass unit or molecular weight unit. Again, it doesn't really matter how exactly it's measured, but I can explain it if you want. And there are polypeptides or proteins that contain as many as 4,000 residues of amino acids. So I want you to get like a scale. So you have a very large protein has like thousands of amino acids, and a very small protein can have like hundreds or tens. And also there are different terms. A lot of time a polypeptide that is less than 20 amino acid in length, we will call it a peptide. Okay? Because a lot of times it's not like this is like a consensus, but it also makes sense because a lot of times, if we're talking about proteins that have this, functions like they're enzymes or they're doing functions in the cell, and they're not just small molecules that are used for like signaling or signaling between cells, then we will not call them proteins, but we will call them peptides. While if we have long proteins, like more than 100 or even more than 20 that have a specific function that we also that are characterized and defined structures, we'll term them as proteins. Okay, so that's a term that's very easy to get mixed up when you see in articles. Sometimes you see polypeptides, sometimes you see peptides, sometimes you see proteins. So it's just a matter of length. So a secondary structure actually is we have three types of. So like I said before, a secondary structure will be determined, like the third structure, will be determined because of the chemical or atomic interactions inside an amino acid, okay, or the flexibility that this molecule has. And a lot of times, because of this, because in the end the amino acid is, at least the backbone is very similar to one another, different amino acids, then they have certain angles that they will tend to arrange themselves into. Okay, and so we will have these basic structures that basic structures in the cell, and these structures will be the alpha helix, beta sheet, or short U-shaped turn. So these are what we will define as secondary structures, and they arise from basic properties of the amino acids, of the conformation of atoms inside the amino acids, that I will explain. Questions? Yeah.
Don't really understand in what way this is hierarchy. Like, what does it mean, primary, secondary? Is it a process in time that happens to the protein? Or
You can think about it as, you write it in the sense of a classic hierarchy, and it doesn't sit exactly in this definition. But in the sense, when you think about, when we try to make sense of when we look at a very long molecule, and we try to make sense of the different components, so we say, in the beginning we have a linear form. That is what comes out of the ribosome, or when the protein is made. And then we have one type of, like the initial type of folding, that arises from local interactions between the amino acid, which we're going to discuss now. So this is the secondary structure. And then we have larger interactions that cause like more folding and more complex folding, and these interactions are between the secondary structures that are formed inside the protein. So it's kind of
deeper into the functionality of the protein.
in a way, it describes the way that proteins are folded, or proteins are made from the initial point when they are coming out of the ribosome, and to the end point where they are folded in the proper way that they should be to be functional. Okay? So the first structure that we're going to talk about is the alpha helix, which is very hard to show here on the model. But basically, the alpha helix arises from the interactions between the amine group, okay, and that attach to this hydrogen, and the carbonyl atom with its oxygen. So we learned last class that we have hydrogen bonds that are formed between hydrogen and oxygen or nitrogen, and here we can see this interaction that is actually causes. So if you think about this like a long strand and you coil it, okay, so this formation, or this structure, is stabilized by hydrogen bonds between the hydrogen that's attached to the nitrogen and the oxygen, okay, over here. So actually what happens here is that because of this formation, all the hydrogen bonds, or all the oxygens, or all the hydrogens, or the free hydrogens are actually involved in hydrogen bonds, and they're not free to interact with water that surrounds it. Okay, so the alpha helix, the fact if this molecule, or this part of the molecule will be hydrophobic or hydrophilic, whether it will interact with water or not, will be solely determined by the side chains of the amino acids that are that are making it. Okay, because all the hydrogen bonds, all the potential hydrogens that can form, or oxygens that can interact with water, are held up by this structure. Okay, so to make this a little bit more clear, let's see if this works. I have no idea what's happening. Okay. It's not showing anything, right? Right. This computer is just about to die, so maybe it's too much for it. Okay, never mind. Just alright, alpha helix. Yeah. Okay. So this is the form that this is one of the secondary structures when we talk about protein folding. Is one of the basic structures that is formed also in the presence of biological environment. Okay, so so we have the alpha helix, and the second basic structure is the beta sheet, which also is stabilized by hydrogen bonds that are formed again between the oxygen and the hydrogen of the amide group, or the nitrogen. And the only difference, as we will see in between this structure and the alpha helix, is actually the angles inside each amino acid. Okay, so the angles the angles will determine like if it's a beta sheet or it's an alpha helix. And the fact that it's the reason it's called like a beta sheet is because of its like planar formation. So you can have very, very large beta sheets that can have form these planar interactions between chains of amino acids. Okay, and they can be also between areas of the molecule that are not close to each other, and it can be also between adjacent areas of the molecule. So let's say in this example, you don't see where the rest of the chain is going. Okay, so it might as well be from if this area of one loop will interact with another loop that is from a faraway part of the same molecule, they will form a beta sheet. Okay, just because of the interactions that are formed between the amino acids. And the conformation that the side groups will take is something like a zigzag, like this. Also, because I told you that this chain has directionality, that we say it's going from the N to the C, we can also define two types of alignments that two of these linear chains can hold, which is parallel if there's the same direction or of the peptide change, or anti-parallel, as we can see like in this example, everything here is anti-parallel to one another. Okay, so just the chain is going from here to here, and then it can cause do whatever it wants here, and then come back here, and interact here, and again a loop here, coming back here. Okay, so you get the general picture. It's just to show you the kind of basic interaction that can happen in the miniature scale, in the beginning. So that's why it's like secondary structure. And we actually have a way, when we look at proteins nowadays, and also this is not a very new technique actually, you can determine exactly the angle or the conformation of each amino acid in a protein. Okay? And you can experimentally find out what are these angles. So, and you can also quantify them. And this is like the Ramachandran plot, named after the researcher that invented this method or this plot. And actually what it comes here to show you is what are the usual angles, or what are the angles that normally will exist inside a protein, between amino acids of a protein, and and inside the amino acid. So, as I told you before, if we're looking at the amino acid, we don't have any rigidity, we don't have any flexibility along these axes, and we also don't have flexibility along the peptide bond. So here the peptide bond will be this link, okay, and this link here. So this will not move, and this angle will be pretty much fixed. But we could still have, and I'll show you on the larger model. So this bond will not move normally, but we can have, because we have the 4 bond formation of the carbon, so we can have one angle that is like this, movement that is like this, and another movement that is like this. Okay? So basically we can define 2 angles, which is phi and c, and you don't have to really remember which one of them is which, but you just need to remember that if I will tell you what is the phi and the psi of this amino acid in the protein, then I can really put it in space in the correct angle, and there's no flexibility beyond that. Okay, so from these 2 angles, if I'll take to each amino acid, I will describe these 2 angles. Then we can actually build how the protein looks like. Okay, and this is actually what you see in this graph that is based on experimental data. Is on one axis we have one angle, and the other axis we have the second angle. How much time? I need to. Okay, after that we'll take a break. So what you can actually see is that this is actually a plot. Each dot here represents one amino acid. Okay, and in something like 10,000 proteins in general. Okay, so that's why you have so many dots here. Okay, so they analyzed the structure of 10,000 proteins and found out what are the angles inside each amino acid inside these proteins. And here they're plotting them like a scatter plot on this axis. So what you can see here, because of these islands actually represent that most amino acids will be in typical angles. Okay, they will not be just randomly oriented like that. They will not have a 360 or 180 ability to rotate along these axes, but they will have typical angles that they will be in. And this angle, the combination of these 2 angles is normally what makes an alpha helix. Okay, what we will call a right-hand alpha helix, a helix that's going like this, and this is a typical combination of 2 angles that makes a left-hand alpha helix, the other way around. It doesn't really matter. And this combination of phi and psi will make a form of a beta sheet. Okay, so what we can see that most amino acids in proteins that we have in cells are in conformation or in structures, in basic structures that are either alpha helixes, beta sheets, but you can have also something that are in between. Okay, and for each amino acid, you can plot this Ramachandran plot and know what are the conformations, what are the allowed angles that this amino acid can be in. And this is determined largely because of like steric interactions. Because what we see here is actually obviously a very simplified model. But what you can imagine is that you have a huge electron cloud here, and also electron clouds all the way around here. So you can't. It's kind of this steric interaction or interference is actually, you can't have like two electron clouds that are overlapping each other. So that's what restricts the type of or the angles that you're allowed to have with like these two angles. Okay, so we'll take a break and we'll continue with that next class. כן. על פי הזווית אפשר לדעת אם זה אלפא או בטא. על פי אם יש לך, נגיד, אם את רואה שיש חומצת אמינו שיש לה זווית פי, שהיא 0, וזווית עם קריסטלוגרפיה. כאילו, המבנים האלה, לא, התנועה זה פשוט... כן, לא, אבל זה פשוט, התנועה זה פשוט להדגים שיש לי יכולת להזיז את זה. זאת אומרת, יש חומצות אמינו, נגיד, אני אראה את זה אחרי זה, כמו פרולין, כן.
אתה מתכוון שאם בגלל זה שאתה יכול להזיז את זה, אז זה עוזר לבדוק.
לא. כן. זה יכול לזוז באופן חופשי. הקשר, זאת אומרת, קשר בודד יכול לזוז באופן חופשי, אבל תחשבי על זה, בגלל זה מטעה, זאת אומרת, המבנה הזה. אז תחשבי שיש לך איזשהו, לא יודע, אטום, שהוא מחובר לאיזושהי קבוצה, ועכשיו הקבוצה הזאת, מימן או, לא משנה, בוא נגיד שיש פה איזה... ועכשיו יש עוד איזו קבוצה שנמצאת פה, אז מה שיקרה, לא משנה, אז בגלל, זה יכול לזוז באופן חופשי, כן? אבל הוא לא יכול לזוז למקום שזה נמצא בו, כי הוא פשוט הולך להפריע לו, כן? כי אז... חומצת אמינו לבד יכולה לזוז יותר, אבל גם יש אינטראקציות בתוך חומצת אמינו. זאת אומרת, ה-side chain, זה מאוד יכול להיות כאילו חומצת אמינו לבד, אבל בגלל שיש לה את הקבוצת צד, אז הקבוצת צד גם לא מאפשרת לעשות כל מיני סיבובים. אוקיי? נגיד אם אני אסתכל פה על הפפטיד, כן? אז אני לא יכול, נגיד, לעשות תנועות, הרבה פעמים אפילו לעשות תנועה כזאת, שמקרבת כאילו יותר מדי, נגיד את שני אלה, היא לא תהיה אפשרית. אוקיי? או נגיד, בטח שלא לעשות תנועה שתקרב נגיד ככה. אבל זהו, יש מספר זוויות שהם יכולים להיות בהן. הם לא יכולים להיות בכל הזוויות האפשריות, אבל יש טווח או אזורים של זוויות, בגלל זה יש לנו את האיים האלה. חומצת אמינו אחת? הם לא חייבים. כן יכול להיות. זאת אומרת, כי אז יהיה אלפא הליקס ואז בטא שיט, ואז, זאת אומרת, כדי שכל החומצות אמינו יהיו ביחד באלפא הליקס למשל, אז את צריכה לכל החומצות אמינו שנמצאות לזה, יהיה את הזוויות שמתאימות בשביל ליצור את האלפא שיט, אוקיי? זה קצת קשה כאילו לדמיין את זה, אבל אם היה לי מודל קצת יותר גדול, הייתי יכול לראות לכם איך זה... כן? כל חומצת אמינו יש לה הפרעה סטרית, זאת אומרת, היא נראית אחרת במרחב. היא נראית אחרת בגלל שיש לה קבוצת צד שונה. בגלל שיש לה קבוצת צד שונה, כל קבוצת צד נותנת הפרעה אחרת. אז כל החומצת אמינו, אנחנו נראה את זה בהמשך, אנחנו נראה את זה בדיוק בסלייד הבא. זה בדיוק הסלייד הבא, זה כאילו מראה לכל החומצות אמינו, מה הזוויות האפשריות שכל חומצת אמינו יכולה להיות בהן. אוקיי? אז...
עכשיו באופן כללי, יכול להיות שאני נשכח כמה מילים.
אין בעיה.
כל הנושא הזה כימיה זה כאילו חדש לי לגמרי.
אני מבין, זה בסדר. כאילו זה...
קראתי על זה, היה לי כל מיני דברים כזה. תהיתי כמה אני צריכה לדעת שאולי קצת יוזמתי, קיבלתי שכאילו אני צריכה לדעת.
לא, את לגמרי, תשאלי, אנחנו לא מניחים שום ידע מוקדם, וגם הקורס הזה מיועד בשביל אנשים שאין ידע מוקדם. נגיד, אם מישהו ישאל אותי כל מיני שאלות שנכנסות לעומק או משהו כזה, אז אני לא אענה לו, כן? כי זה לא המטרה. המטרה כאילו לתת לכם... המטרה זה... שוב, גם אנחנו לא מצפים שאת בסוף תביני את כל הדברים האלה ותזכרי בדיוק מה זה אומר, כאילו רמת צ'נדרן פלוט עם איזה זוויות, דברים כאלה. אבל זה יותר כאילו בשביל להבין את השפה, כאילו להבין על מה אנחנו מדברים. אוקיי. כן. אין בעיה.
זה היה קצת לפני, בוא נראה את א', זה כאילו A ו-B הנה, לזה, לא הבנתי את ההבדל בעצם?
זה פשוט מבט צד. כן, זה אותו מולקולה, את פשוט מסובבת. לא, זה פשוט מולקולה שהיא מסובבת. אז פשוט מסתכלים עליה מהצד כדי לראות את הזיגזג הזה של החומצות אמינו שנמצאות בקונפורמציה כזאת. עכשיו מבינה ברגע שהחומצות אמינו נמצאות ככה, יש פשוט, יש זוויות מסוימות שהמולקולות האלה נמצאות בהן, שהן שונות מאשר הזוויות שצריכים בשביל ליצור מבנה כזה. אז זה בדיוק מה שזה בא לתאר, הרמת צ'נדרן פלוט. כאילו זה הקומבינציה של הזוויות שיוצרת אלפא, וזה הקומבינציה של הזוויות שיוצרת בטא.
gets returned via these regular patterns. And there are four different types of regular patterns. We have alpha helix, we have beta pleated sheet, we have beta term, and we have omega loop. And these four different types of regular patterns are composed the secondary structure of our protein peptide. Now the question is, how exactly does the polypeptide switch to form these four different types of structures? Well, inside the polypeptide is the different bonds. Now, the peptide bond is a bond holding the amino acid inside the polypeptide together. And these peptide bonds have a double bond pattern. And what that means is they don't but for the other peptide bonds inside the polypeptide, these rotate. It's the rotation of these double bonds inside the polypeptide chain that allows the linear polypeptide to eventually flow into the beta pleated sheet, into the alpha helix, into the beta term, and our omega loop. Now, once we form these regular patterns, the question is, what exactly stabilizes these structures and allows them to exist in the first place? Well, it's the hydrogen bonds that exist between the amino acids in that polypeptide chain, as we'll see in just a moment, that allows each one of these secondary structures to actually exist in the first place. So let's begin with the alpha helix. So what exactly is an alpha helix? Well, an alpha helix is formed when we have our polypeptide chain, and that polypeptide chain begins
Did everybody come back?
a rod-like structure.
Yeah?
And inside that rod-like structure,
Okay, so how are you holding on? You okay? I know it's it's a lot of terms, and normally there are courses, okay, entire courses in biology when you learn this thing. So so it's good because we're going slow, because now we're doing things that are more complicated. So it's good that it's better than last time. Okay, so we said that a way to quantify, this is a descriptive plot that actually shows us in which conformation, in which angles we normally have in the proteins that are normally in the cell. Okay? And we can see that most of the conformation are the angles, the combination of these two angles is fitting as an alpha helix or a beta sheet. This is another alpha helix, and you have all sorts of other areas, but most molecules are either in most conformation of amino acid will be normally or either in alpha helix conformation or in beta sheet conformation. So actually we can do these plots, and this is a theoretical plot actually, but actually experimental. It's very close between experimental and actually theory. Hassan, מה זה הבירה? Okay, so this is a test to see if you can understand. If you can understand like what it means, this Ramachandran plot. So these are 20 Ramachandran plots for the 20 amino acids. And what I said is that the side group that we have here, this model is very simplistic. Actually, you need to imagine everything a lot more bloated. Okay, everything here is like buzzing electron clouds that are interfering with one another, and thus, if you have an amino acid that has like a large side chain or a very interfering side chain, then it will restrict the angles that the amino acid can take. Okay, or the two angles that can rotate freely. So, for example, if we have like a huge, if you imagine like this amino acid that has, let's take the other one, that has like a huge group around here, then this rotation, like a rotation that is like this, could not happen because you'd have like interference. So this will have to be planar in order for it not to interfere with the cloud of the other one. So I mentioned in the last class we have like the two special amino acids that we have. One of them is proline, and the other one is glycine. What is special about proline is that, so actually I made a proline for you. So this is actually how it, someone detached Did you detach the proline? Never mind. Okay, so we have, this is the alpha carbon, the carbon that has, and this is the side chain.
are single bonds, and they do
And just to make it clear, I'll show you.
that allows the helix and the other structure,
So,
secondary structure,
and in general,
to form in the first place. Now,
this is where,
it's the hydrogen
so this is how it's incorporated inside like a chain.
of
Okay,
one
no,
amino
actually it's okay.
acid, and the
This is the way it's incorporated inside the peptide chain. So think of my hands that are other amino acids, and you have this amino acid. And like I told you, so
let's focus on
in contrast to a different, now this is this formation, because of this loop that is formed between the side chain and the amine group, and the amide group, which is the nitrogen over there. Do you see it? Like this.
what is the numerical
Okay. It actually restricts the possibilities of the angles that this amino acid can take. Okay. So can you try to guess which of these Ramachandran plots is describing proline?
amino acid number 3, and finally you have this peptide here, and amino acid number 4.
So we said that the two angles are around the carbon atom, the alpha carbon, and this is the alpha carbon. Okay. So and I said that this angle, this movement, is one of the angles, and this angle, and this is the second. Okay. So as you can see, it's very hard for me to even move these. Okay. So and this. Actually, I'll give you a hint. Okay. So as you can see, there are actually more or less two conformations or two combinations of these angles that can actually take place. Like one of them is this, and the other one is just like this. Okay, you see, I'm just tilting them between two states. So you can have only two states or two combinations of angles that can exist in this molecule, and everything in the middle, like this transition state, is actually non-stable because it causes like stress on the actual bond. Like if it was like metal, not plastic, I wouldn't be able to do that. Okay, to do the like the middle. So and the nitrogen, okay, which is the blue. Okay, so normally in a peptide bond, this side chain. So in proline, you have a side chain that is connected here instead of one of the hydrogens. It's like connected here. So this is what we have. This is what we have here. So can you imagine like what kind of a Ramachandran plot will describe the allowed angles or the angles that proline can take? Which one of these Ramachandran plots is describing proline? Okay, so the color means like if you have a deeper color, it means that this will be more common. Okay, like a deep color will mean that this angle, like let's go back to the other one. So most, as you see, like there's a very black cloud here. So this will be like red in the plot before. So these are like contour lines. Okay, so you can sketch like contour lines around. What it means is actually that for most amino acids will be around here, like this combination of the two angles, and some of them will be here, and then some of them will be here. Okay. So let's say we're now taking all the prolines from all the proteins, and we want to see what are the angles that proline can have. Okay, that proline can have between, like we said, that the two angles between the alpha carbon. Do you have a guess? So this one? This one? How many people say this one? This one? This one? This one? This one? This? This? Okay, so it's this one. So I hope through the I'm not expecting you to be expert in Ramachandran plots, but I'm trying to, through the examples, to let you like get an intuition about what this actual plot means. Okay, so because we have these small circles or small areas, we have only specific angles, specific combination of phi and psi that are allowed or that this molecule can exist in. Okay, so this is exactly why we have the reason that we have two is actually because I showed you that we have like two options of conformation that we can have. So like this cloud, now we have like specific angles, so it will be these angles like this and this, and if I tilt it, then we'll have like this and this angle. Okay? So this is proline. So in contrast to proline, this is a hint, we have another amino acid that is glycine. So glycine, what's special about it is that it doesn't really have a side group, and the side group is hydrogen. So it's a very small side group. If it's a very small side group, then what will it mean in terms of steric interference? Will this side group cause a lot of interference, or wouldn't cause a lot of interference? So it won't cause a lot of interference. That's the angles or the types, like the conformation that the molecule can take, are actually less restricted, right? So that the angles that this molecules can be in it has a wider range of angles that it can be in. So which one of these do you think is representative of glycine? This? Right. So as you can see, you would first of all, you can see that there is steric interference, and not all angles are allowed, or all angles are possible, but still there are a lot more areas than other amino acids which are more restricted. So this actually is true. So we have glycine and proline. Okay? Again, if it's not sitting entirely correctly, it's okay. You don't have to be expert on channel plot, just to understand that certain angles form certain structures. Okay? No, we didn't talk about U-shaped turns. Now we're talking about U-turns. So U-shaped turns are actually like they're less special in the sense of the specific angles. We just term like these like turns or sorts of like if the linear form does like a very sharp turn, then we will call this a U-turn. But there are specific amino acids again that we will normally find in this U-turns. And can you actually it's written here? Yeah. Okay. So never mind. But one of them is again glycine, but it's in the U-turn because it can get all sorts of very sharp angles, so it's very flexible. And the other one is actually proline, which is not flexible, but it has an intrinsic turn in its structure. Okay, so now because it's ruined, I can't show you, but yeah. So this is actually opposite. Okay, so these are actually the two. If we're looking at proline, so these are actually where the next amino acid will come here, and the previous amino acid came here. So you see that there's an intrinsic turn in the shape of the molecule that actually everywhere that you have proline will inevitably make like this U-turn. Okay, because of the rigidity, and glycine just allows it. Okay, because of its flexibility. And here are like examples of what you see. These are how people normally draw beta sheets, and this is just here you have more beta sheets, and this is just like an upper look on a protein that has this cylindrical shape. Okay, so all these are beta sheets. They're normally depicted like this. Okay, so we talked about basic secondary structure. We have the alpha X and the beta sheet, and now we're going to talk. Yeah. A beta sheet is normally defined as the interaction from here to here. So this is not part of the beta sheet, but obviously you need turns to create the beta sheet. Like in this example, you don't actually need. It's just like round. But here you need the turns to, but only this area is defined as the beta sheet. Okay, the part that is in red. You can have both. When it's opposite, we call it an anti-parallel beta sheet, and when it's the same direction, we call it a parallel beta sheet. Okay? But it doesn't really matter for you. So we're talking about secondary structure. So tertiary structure is actually the final folding of a protein. That it's actually the way to describe the 3D formation or structure of a protein, or how it folds, is its tertiary structure. Is actually how the protein looks like in the end. And in contrast to secondary structure, most of the time, because we're talking about large formations, so you need to think about a lot of alpha helixes and beta sheets and turns that now are like folding together to form this complex molecule. Then most of the interactions will be like hydrophobic or hydrophilic interactions and not like hydrogen bonds. But you can have certain hydrogen bonds, but because we're talking now about like a larger scale of folding, then the backbones of the amino acids will not come together very close to form like hydrogen bonds with each other, but the side chains can. Okay? But generally we're talking about, you need to like, as I said, you need to imagine a lot. Okay? In this course, you need to imagine like that now we're talking about like a larger scale. So after you have the initial folding, then you have secondary folding, which determines the final structure. But because the structure is not strictly stabilized by hydrogen bonds, like exact connection between like two molecules, then it allows a lot of flexibility. Okay, so I said in the initial class that you need to imagine that that all the molecules and everything and all the proteins are moving constantly. Everything is like in a certain like shaking state. So also a protein, when you look at a protein, for example, so here we have just rust. It doesn't really matter what it does, and it's bound to a small molecule here. So these are just different ways to show proteins and how you will see like normally proteins in articles and stuff like that, or in textbooks. So this backbone trace, it's named just the name of the display. All of these are the same proteins. They're just shown in different ways. Okay? So in this way, they just show the backbone of the amino acids. They don't show any side chains or any hydrogen sticking out. They just show, if you want to look, they just show here this line, okay, that's going through here. So this is why this structure is very simple. Okay, so a lot of people, it depends what you want to show. Obviously, you will choose a different representation. Depends on what you want to show. But this only shows the backbone of the peptide. The blue area is a different molecule, it's a GTP molecule that is bound to it. This is just like this is an example of an enzyme. So there are a lot of time in an enzyme they show the substrate with the enzyme, but we're going to talk about it later. Okay, so you can just ignore the blue. This is what we call a ball and stick. It actually shows all the molecules. Okay, so like I'm showing you here, it just shows every single molecule that this structure has. This is very complex, as you can see, and obviously you don't see here like the structure that we talked about before, about the alpha helix and beta sheets. The ribbon structure is a lot of time what you will see in articles. A lot of people choose either this or this, but here it's very easy to see that you have, and you also have like different colors. So the red here are all the alpha helixes, and the blue are all the beta sheets. Okay, so now you can get like a little bit sense of the hierarchy that we talked about before. So you have the secondary folding creates these structures, and the third level of folding, or the tertiary structure, is like a folding of the secondary structures. Okay, and this is actually the protein. This is how the protein looks, and because we know what these means, then we can understand more about the interactions and what happens, what is the function of this protein and what happens here. The last view, which I actually like, for me, I like the most, but this is not based on anything, is the real life, how the protein looks like. Okay, so here you see actually all the electron clouds. So like I told you before, that here I don't show you any of the electron clouds. This is how the molecule is, how other molecules see this molecule. Okay, in general. So this is if you would turn really small and you would get inside the cell, then this is what you would see. Okay, you see these clumps that look something like this, but obviously from here it's very hard to understand what are the basic structures of the molecule. But this is how it looks, and here the colors represent charge. Okay, because I told you that you have amino acids that are positively charged, negatively charged, polar and nonpolar and stuff like that. So in every protein you have like areas that are negatively charged, positively charged, because the amino acids that are sticking out of it. And also this is the first time that we see a protein that is folding. So we can imagine that the amino acids that we will find in the center, in the core of the protein, will be hydrophobic or hydrophilic amino acids. What do you suspect? They will be hydrophobic, okay? Because they will tend to be repelled or not interact with the water, so they will be in the center. So that's why also water interactions are very important for this folding procedure, because the water actually chooses a certain conformation of the folding of the protein, okay? Because of these interactions. So all the hydrophobic will be more or less in the center, and the hydrophilic will be in the surrounding. Okay. Now we're starting to get into more like terminology, so it will be like a little less clear cut. But all of the things that we're going to talk about now are like how people like to define functional groups of proteins. So we define the groups as structure, like alpha helix or beta sheet. But proteins, because they do stuff, right? So you can take a protein and divide it into functional groups that have a specific structure. Okay? And this, I think, will be more. Blah blah blah. This is not interesting. Okay. So what do I say when I say protein motifs? Or these are examples of very common protein motifs, or you can say typical conformations where you find or organization of a polypeptide chain or a protein that has a specific function. For example, if you have a protein that has to bind calcium, you'll find in the majority of cases you'll find a motif that is called helix loops helix motif. So you see a helix and a loop and a helix. And this motif is very, what it can do is bind calcium, okay? So in a lot of proteins that can bind calcium, different proteins, you will find a structure that looks something like that, okay? And a lot of time, yes. A lot of time, if you have like, if it has to be a channel, then it will look in a specific way, and it has to be a signal molecule a lot of time, or it has to bind a specific ion, it will look, or it has to absorb photons, then it will look like a like an opsin or something like that. So a lot of time, and in biology you can always find, like, you can never say always, okay? Because you will always have exceptions, okay? And this brings me to also the notion of consensus sequence. So this describes this structure, and the letters are actually saying which type of amino acids we can have around this area. Okay, so you have this. This is like the consensus sequence, or the type of amino acid that you will normally find in a motif that binds calcium. So you will have either the D amino acid or the N amino acid in this position. The next position, it doesn't really matter what amino acid you have. Then the next position, you have either a D or an N. Next position doesn't matter. Next position, you're going to have or a D, N, or S. Then you have this backbone. And then a few positions, it doesn't matter. And in the end, you have a E or a D. So it means that in most proteins, in the vast majority of proteins that have this structure that bind calcium, you will have specific amino acid in specific locations, okay? And you can have a certain flexibility. So let's say in this formation, that zinc finger motif, a lot of times you find this in proteins that have to bind DNA or RNA. We'll have this zinc finger motif, and the consensus sequence here is a little bit more rigid. Okay, you have to have this amino acid here, this amino acid here, this amino acid here, and this amino acid here. Okay, and this is actually what this consensus sequence means. Okay, it depicts the position and the identity of the amino acids that you need to have in order to interact with calcium, interact with DNA, interact with one another, like in this example here. Questions? Okay, so the second type of, so this is calcium binding, like I told you. The second motif here is a zinc finger motif because it binds, it uses, it has a cofactor. This is not part of the protein, okay? It's just an ion that helps the protein do what it has to do, which in this case is normally bind to DNA or RNA, okay? So this structure facilitates binding to DNA and RNA. And this structure is actually, you have a helix that in one side you have like in the mid. So these are two helixes actually, right? They can and in the middle you have all the amino acids that you'll find in the middle here are hydrophobic, and all the amino acids that you find in the outer area will be hydrophilic. And what the structure can actually do, you can imagine that these two as like the center is like two droplets of oil, like we said before, that they tend to attach to one another. So they have a lot of, so the entropy or the energy, the free energy in these two structures will really tend for these two formations to cling to one another. Okay, and it happens in a very rapid way, in a very energy favoring way, and it doesn't require any other like ATP or cellular energy to be invested in that. So can you imagine, like, when would you want like two very strong thin elements to bind to one another in a very rapid and strong way? Can you imagine like a cellular function that would be good for that? Well, it's difficult, it's not trivial, but these are elements that normally you would find in fibrous proteins, a protein that makes skeletons, like the skeletons inside the cell. Like inside the cell, you have a lot of proteins that are actually like the backbone. So we refer to them as the skeleton of the cell, or cytoskeleton. Okay, so the cell, because it's very dynamic and a lot of time has to change, so it needs to have a lot of these molecules together will form like a fiber, okay? And more special, it's like a self-assembly fiber, okay? That will like assemble by itself, and also you can take it apart if you introduce energy. So we will see it. Okay. Now we talked about motifs. Yeah. So you tell me. Yeah. So we talked about protein motifs. Now we're going to talk about protein domains, which in general a lot of times they're interchanged, like the two terms, but it's all is in the size. Okay, domains are when we talk about domains, we're talking about large structures. Okay, so let's say we have a huge protein, and we want to describe what kind of areas we have in this protein. So let's say we have our area that looks more like a ball shaped, an area that looks more elongated, an area that looks, and we want to describe or divide the protein into different areas. Okay, so we will call these areas domains, and an example is in this protein, hemagglutinin. So we have a globular domain that just looks like more like a bolus, and a fibrous domain which is composed of more long chains. Okay, and a lot of times the domains have a lot of proteins have the same domains that have also the same functions and made of a lot of domains. So, and normally we'll discuss domains when we talk about very large proteins that have a molecular weight that is relatively large, and we need to decipher them as different domains inside the same protein. So, for example, like this, here we have 3 proteins, each one of them in different color, okay, which will lead us to the next classification of a lot of subunits that are not the same molecule. Like I said, this thing is like the same molecule, and here we have like 3 molecules or 3 males or 3 monomers that are coming together to form like a functional large protein. So just an example for if we're talking about how you will see it in textbook a lot of time, if we have a motif or a domain. For this example, is that we have a domain that looks like an EGF. So EGF can be like a protein by itself. It has functions along the cell, but also it can be other proteins can have EGF domains. Okay, so you can have an independent EGF protein, or you can have an EGF domain as part of a different protein. Okay, and a lot of times they will have like the function will be completely different when it's inside a different protein, or it can have similar function like the protein alone. Okay? So this leads me to now we're actually done with all the structure that all the definition of the structure that describe the same molecule. Meaning, when I say the same molecule, I mean that all the elements are covalently linked. Okay? And now we're going to talk about, but actually proteins are a lot more complex than that, and a lot of proteins are composed, or functional proteins like channels or receptors are actually made of multiple subunits of similar, or maybe a lot of time non-similar proteins that are like coming together to form one protein. Yeah. Bond.
So once again, hemoglobin is the tetramer that consists of 4 individual subunits. Each subunit is equipped with a hemoglobin.
Between molecules, no. You have, yeah. When hydrogen bonds, like for example, are not defining the molecule. Okay. So. Okay. So, for example, we'll take the hemoglobin. And this is like the ribbon representation, like I showed you before. So, functional hemoglobin in our body, which is the molecule that is responsible for carrying oxygen in our blood. So it's made of 4 more or less identical, but not really identical units of a protein of globin that are like held together through a lot of interactions that we talked about also before. You have electrostatic interactions, you can have polar interactions, you can have hydrophobic interactions that will bring all these components together to form this functional large protein. So this is like the quaternary structure. Okay, so it's different. It's like multimeric protein. This hemoglobin, and the last level is what we call macromolecular assemblies, and this is very like biased to the definition of how people will define it. But in general, this representation is used to describe a group of proteins that doesn't have to be related to each other in structure or anything else, but a group of proteins that act together to achieve like a certain cellular goal. Okay, so for example, if you want to transcribe a gene, like to convert or to transcribe RNA from DNA, which is a process that is very important, obviously. And then we need all these factors together. Each one of them is doing a specific role and and they bind to each other and they do all sorts of interaction to each other. And all of them are critical in order to extract this cellular process. Okay, so we need like some kind of protein that will unwind the DNA double helix. You need one of them to bind to a specific location to show where the gene is starting. You need another one to make the RNA from the DNA, and so on and so forth. So these we will define it as like the fifth hierarchy, as like complexes of molecules. It can be like very like huge complexes that are containing like hundreds of proteins that are acting together for a specific cellular function. Okay? So, in order to make sense in all this, I thought about a good way to show it. I'm not sure it's very good, but it's the best I can do. So, all of us know the Power Rangers, right? So, Power Rangers, they can all act separately, right? Normally, they're not doing a very good job in that, but each one of them is like independent. So you can think about them as like independent. Actually, like in proteins, that's why the metaphor is not really exact. But you can think about them as monomers. That if they want to really do something together, they need to form a megazord. Okay. So the megazord, as you know, is not covalently linked. They can detach from the megazord. They don't, obviously, okay? It goes beyond saying. So you can see that this is like the part of the yellow Power Ranger, this is the part of the blue Power Ranger, and all of them are like put together to form like a functional protein, okay? But they're not the same molecule, right? Because each one of them is unique and has a specific like character and problems and stuff like that. And also, in some cases, so this is like the fourth level, and this is like the fifth level, where you can have like a cooperation between two megazords. I actually don't remember how this megazord is called. If someone knows, then it's good. But they can work together to achieve like a goal. And also, what is very common especially in like receptors, is that you can have like, let's say you need this combination of subunits to form this protein, but you can have a different combination with other proteins to make a different protein. Okay? So you can have the same subunits together with another subunit, I would say the white Power Ranger, and it makes a different megazord. Okay? Than the other one here. Again, they're not covalently linked. And I had a video that showed it in a very scientific way, but the Power Rangers, obviously. Let's see if it works. I'm not sure. I don't know why it's not working. I don't understand it really. Maybe they blocked it or something like that? You're hearing it, but you're not seeing it. Anyway, it would have been nice. Okay, it was funny, but never mind. So this is like a summary of what we learned about protein in the sense of like hierarchy, and just a small part like about protein evolution. So generally, when we think about evolution, most of the things that we think about, like our cells that we evolved from, some kind of animal that's common ancestor with the apes or stuff like that. But in general, what undergoes evolution a lot of time, if we think of evolution as changes in our DNA and thus changes in our proteins, then the proteins are the ones that are going through the evolution, and we can, like we're building for different people, if we're comparing their DNA sequence, we can know what are their ancestors. We can do the same for proteins and devise this like evolutionary tree. So, in the example of hemoglobin, for example, which is the oxygen binding molecule, you can see that if we take like hemoglobin or globin units this is the example of the beta unit of the hemoglobin. So hemoglobin is made of 2 beta units and 2 alpha units. All of them are capable of binding oxygen through the hem group here. And if we're looking if we see, for example, so we have hemoglobins that are almost similar to one another in different species. In this example, it's actually plants. Okay, contrast to what a lot of vegetarian people think. Animals also breathe, so they have oxygen binding capacities. And their hemoglobin is very similar to our hemoglobin, but it's not entirely identical. Okay, so the sequence of the amino acid is changed, but it's not changed. The sequence of amino acid is similar, but it's not. It's not equal. Okay, and the structure is very much similar also, but it's not equal to one another. So these different units that are similar but not exactly the same, we will call homologs. Okay? In our evolution, for example, the hemoglobin alpha unit and the hemoglobin beta unit are like a recent split in the evolutionary tree to form these different subtypes of globin that are interacting together in the same protein. And how much time do I have? I don't have. For sure we didn't get to enzymes, but. So I guess what do we have here? This is folding. Okay, so I'll just describe this. This phenomenon because it's related to what we said before. So in general, foldings. If we're talking about how a protein folds, and we're talking about in vitro environment or an isolated environment. A protein can have almost like an incredible amount. I don't want to get into why this number is the amount of possibilities that a certain protein can have to fold to form like a three-dimensional structure. But what we actually see in vivo is that every protein, every sequence of amino acid normally falls just into one form of the different types of form. Like let's say we have this polypeptide chain, so I can just fold it like this, or I can fold it like this. I can fold it like an infinite possibilities of ways for it to fold, but still in the cell we'll find just one conformation for each amino acid sequence, or for each polypeptide. Okay, and this state that normally we'll find the cells is it's called the native state. And the reason for that is also related to a lot of things that you will learn in LSEC, is because it's actually descending in the direction of the free energy. So the native state, or the native structure, will be the one that is more energetically stable in terms of entropy and free energy. So it will, from the beginning where it starts in a linear form, it will fold, and on the way it can get all sorts stuck in all sorts of misfolding. A lot of time it leads to disease. But in the end, and we will learn in the next class exactly we'll learn about a group of protein that actually helps the protein fold in the correct formation. It also catalyzes and makes this process very fast. In the end, in a normal state, a protein will fold in a specific conformation, in a specific way, out of all the possibilities that it has. Okay, so for example, if you have if we have like an egg or something like that, I have to put for the end some examples from my cooking. So let's say we're now what is actually happening when we're boiling an egg? Okay, when we're boiling an egg, when the protein in the egg crosses 70 degrees or 65 degrees, what happens is actually that we're denaturing the proteins there. Like all the proteins there are folded in a specific way. And what's happening in 70 degrees, what happened normally to proteins, that the energy is so large, the energy that we introduce through heat is so large that we cause alternative. So we're actually, you can imagine that we're jumping out of the valley that will reassemble the protein in the proper way. And because we're introducing energy, we're actually causing the proteins to interact with each other. The linear forms of the protein will start interacting with each other and fold in a way that will cause them to aggregate. And that's why when we heat an egg for more than 70 degrees, it will form a rigid structure, because this is actually the interaction of all the linearized forms of the proteins that are interacting with each other, when normally, if the egg is not cooked, then all the proteins are in their closed condensed state that are not interacting and not aggregating with one another. Okay? Question? So you should not exceed more than 70 degrees. A lot of times if you want the egg to be cooked properly, then don't cook it too much, because then, yeah. Okay, so I will give you the questions. You'll see the questions in a few hours. On the web page, I already put this presentation there.
And we'll continue with chapter 3.
Yeah, and we'll continue with the other part of chapter 3. Next lesson maybe we'll go a little bit faster, but yeah. And after next lesson, I will give you the first article about NMDA receptors, and then we'll discuss it in the fourth lesson. כן.
מה בבטא? כי בבטא לא כולם.
בבטא לא כולם, אז הרבה פעמים, כן. כן. כן.
המבנה הרבעוני, כאן זה אותה תת יחידה. כל הזמן, זה מבנה רבעוני.
כן. כן.
Thank you.
No.